Welcome to the video of our NIPS 2018 paper, HOGWILD Gibbs can be pan-accurate. Our work deals with sampling high-dimensional distributions described by graphical models using a shared memory multiprocessor. A graphical model concisely represents the dependencies and structure of a high-dimensional distribution. In this work, we are interested in getting samples of n-dimensional distributions described by graphical models for very large n. A canonical example of a graphical model is the Ising model, which was first used to model magnetic systems. In this model, each xi takes a spin of plus or minus 1, representing spin up and spin down. The probability mass function for the Ising model is shown at the bottom of the slide. The theta values on the edges of the graph represent the strength and sign of local correlations. Graphical models are hard to sample from directly, and thus samples are generated by running the Gibbs sampling algorithm that mixes to the desired distribution. Gibbs sampling starts at an arbitrary state x. In each iteration of its loop, it chooses a random index I from 1 to n, and resamples xi conditioned on the setting of all the other variables xj. While this process could take exponential time to converge in general, it converges in n log n steps under de Bruijn's condition. In the Ising model, de Bruijn's condition corresponds to the high temperature regime, meaning that the sum of the edge weights around any particular vertex are bounded by 1. The algorithm has a plethora of applications in inference, statistical physics, bioinformatics, and more. Gibbs sampling is often run on huge graphical models in practice, and many of its applications benefit significantly if the algorithm could be run faster. The HOGWILD paradigm is targeted at exactly that. The HOGWILD algorithm speeds up Gibbs sampling by running update steps in parallel on a shared memory multiprocessor. To ensure a high throughput of operations, the algorithm runs in a lock-free manner. However, the lock freedom gives rise to race conditions. In particular, stale reads can occur when a process overwrites memory that another process is using. This brings the correctness of the algorithm into question. To understand the behavior of HOGWILD, New et al. Proposed a now popular stochastic model for asynchronicity. In this work, we study the accuracy and bias of HOGWILD in estimating statistics of a graphical model. Our results build on the previous work of Dikkala et al. In 2016, they showed that HOGWILD estimates marginals of the desired distribution accurately. In particular, for any small subset S of the n variables, Dikkala et al. Proved that the total variational distance between the true and HOGWILD distributions on the variables of S is small. However, their bound becomes trivial when the subset S contains even a constant fraction of the variables of the model. We focus on statistics of all the variables. We proved two main theorems. 1. For any graphical model satisfying de Bruijn's condition, we show that HOGWILD can be used to accurately estimate the mean of any Lipschitz function to an additive polylogarithmic accuracy. 2. In the specific case of high-temperature Ising models, we show that HOGWILD can be used to accurately estimate degree d polynomials to an accuracy of n to the d-1 divided by 2. This is quadratically better than the n to the d-1 bound that we can obtain just based on the Lipschitz result. To prove our results, we couple a HOGWILD chain with a sequential one, to get a bound on the Hamming distance between their states. We then leverage recent concentration bounds for graphical models from the work of Daskalakis et al. And others. We verify our theoretical results by running experiments on a 64-process shared memory machine. The first set of experiments in our paper, which are not shown, validate our stochastic model of asynchronicity. The second set of experiments shown here compute estimates of the complete bilinear function over 5,000 HOGWILD samples for two different Ising models, one on a complete graph and another on a degree 4 graph. The plots show that the HOGWILD estimates consistently fall near the true values. The error bars in the plots are computed from our theoretical estimates of HOGWILD's bias and thus validate the theoretical results. To learn more, come view our poster at NIPS 2018 at this location.